Hello, everyone. Thank you for joining us today, this evening, for a very exciting program. With a very exciting, leader in aerospace. You can see Stratolaunch. Everybody very excited. I know everybody is so excited, so we don't want to take you too much time. So we will just go straight into the event. But before that, we have a few words, for logistics. So basically, we appreciate AIAA headquarters to provide for providing this wonderful Zoom platform. And this event is recorded thanks to Stratolaunch, and it will be posted after the event. So if somehow you got disconnected, please keep trying. It should be temporary. If bandwidth is a problem, please try to use dial-in. And I won't read the detailed bio. But Dr. Zachary Krevor is the Chief Operating Officer of Stratolaunch. He's also AIAA Associate Fellow. You'll hear more from him as it goes. And we have Colonel Thomas, is the Director of Flight Operation, also from Stratolaunch. He's our AIAA Senior Member. And to complete the picture, we have the engineer, Mr. Hutchison, is the lead engineer at Stratolaunch. So please enjoy the event tonight, and we're so excited. So welcome, all three of you. Dr. Krevor, so go ahead, it's all yours.
All right, thanks a lot, Ken, and I want to thank the AIAA Los Angeles, Las Vegas section for hosting us. I see a lot of familiar names out in the audience, so good evening to all of you. Thanks for that very nice introduction, Ken. So as Ken mentioned, my name is Zach Krevor. I'm the Chief Operating Officer for Stratolaunch for this latest incarnation here. And what we are offering is flight test services for the hypersonics community. So Ken, if you could go to the next slide, slide 2. Just a little bit about us. So we have transitioned from a ownership under Mr. Paul Allen. Our current owners now are Cerberus Capital Management, so they're private equity group that owns us. And so what we are trying to do is bring hypersonic test services to the aerospace community. We're fully funded through hypersonic flight tests. I think a number of folks are aware our facilities are out at Mojave Air and Spaceport. That is now our headquarters. We have transitioned from Seattle down to Mojave. And as mentioned, that's our offering down there. And we have two great folks here to talk to you about some quite a few more details. If you go to the next slide, Ken. So I'll help Ken moderate here. Really, probably quite off the bat, the immediate questions: when are we going to fly? So goals to fly carrier aircraft again later this year. Goals to start our hypersonic flight tests next year. But all bets are off with COVID, just like everybody else. We've been significantly impacted by COVID, so that's my caveat for us there. So we flipped around the agenda just a little bit due to the flow. We have a lot of slides. I'll help Ken moderate it here. I think folks will really have hopefully a very interesting time. I know we talked, I think 2 or 3 years ago with one of our younger, I'm not supposed to say that, I guess, less experienced engineers, but folks will hear from both Mason and Evan, who've been with the program quite a bit. Were instrumental in the first flight, of course, and I think folks will really enjoy today's presentation. So with that, Mason, why don't I turn it over to you? Let's get going. I'll stop talking.
All right, thank you, Zach, and thank you to AIAA for allowing us to join you tonight. I need to share my screen. Okay. And do you see that screen? All right. All right. Well, good evening, everyone. I'm Mr Hutchison, and I'm with Stratolaunch LLC in Mojave, like Zach said. I'd like to first start by thanking AIAA for inviting us to this event for this special webcast. And also thanks to Stratolaunch for supporting AIAA in its mission to ignite and celebrate aerospace ingenuity and collaboration. And as advance on this one. Here's a picture of myself with the airplane right before flight 2. And this is it taken in Mojave, California. I started my career with an adventure through model aviation, and I've been a model aviator my entire life. As a matter of fact, Stratolaunch enabled me to appear in my favorite magazine, which is Model Aviation Magazine in 2020. Big opportunity, in my opinion. I came on board for designing the mechanical flight control system, and I've been here since the very first roll of carbon fiber fabric showed up to build the airplane all the way through to today. So I've been present for each of the 2 flights and involved with the design and build of the airplane every single month of its progress. I am a lifelong aviator and have got my roots in working in Mojave with scaled composites. I have a lot of experience working with landing gear and systems, so I'm a systems designer. And what are we here to talk about tonight? I am passionate about the Stratolaunch carrier aircraft and being an engineer on the program. I enjoy getting to, and I enjoy getting to work on all areas of the program. This is the Model 351 Stratolaunch carrier aircraft, originally built by Scaled Composites. Although we're no longer part of Scaled Composites, Stratolaunch is a standalone company, and this is known as the Stratolaunch aircraft. And our current mission is to offer the high-speed flight test services that Zach just mentioned. So what's the purpose of this aircraft? Simply, your payload goes here. The original design of this airplane was to haul a payload, and it's an air-based launch platform that will make access to the hypersonic test conditions more convenient, reliable, and routine. The payload is centrally located between 2 tall fuselages and under the wing, giving it the clearance for large payloads such as rockets to carry at a high altitude. So the baseline launch mission when we first designed the airplane and at the start of the contract was to reach the capability of taking a payload on a 1,000 nautical mile radius. That includes 2 opportunities to loiter before and after the release of the payload. The Stratolaunch carrier aircraft, from the start of conceptual sketches until the first flight, was intended to carry rockets to an advantageous altitude that would allow for launching from flexible locations. That's the big advantage. The current program won't require the pull-up and release maneuver that you see here in this, but understanding the safe separation and careful mitigation of the associated risks with separation is where Stratolaunch shines. So let's talk a little bit about the big launcher history first. We didn't come up with this idea. This is an old idea that's been around for a long time. Let's start with the 1940s. That is an original Hughes aircraft concept, and it kind of looks familiar. It's starting to look a little bit like the Hughes H-4 Hercules that we all know and love. Finally, later on in the 60s, of course, we needed a way to carry the shuttle 747. So as concepts were entertained, check that out. That's a C5, twin-hold C5 concept. Can you imagine how big that monster would be? Because we all know how big C5s are. It's interesting to note here that this configuration of the C5 actually has less space between the fuselages than our configuration at Stratolaunch. And also note the inboard engines in between the fuselages. So that wing joint and that complexity, clearly not a contender for an economical path to flight. So let's move on to the top launch 747 that we're all familiar with. This low wing design was favored over the high wing design of the C5 concept, mostly because the lack of mods that were needed. While there were still considerable mods on this aircraft, the pressures that contributed to the success of this design were indicated by the fact that the Air Force would retain ownership of the C5s, but NASA would have operational ownership over the 747. And that was a big advantage that drove them towards considering the top launch idea. Notice the cheat lines from the American Airlines livery. You see a theme there? Using an airliner to accomplish the big launcher concept. That theme continues throughout this presentation. So the top launch was deemed risky and more variants were offered in the process. So here's a shuttle carrying concept that moves the wing of the 747 to a high wing position. And notice there's a straight section in the center line span to simplify that connection. But still, extensive structural modifications is the obvious obstacle to this concept. I found this as a wood model on eBay that I really tried to win and I actually lost. Neat little artifact. Okay. So as the launcher progression of the history of launchers go, there became an economical aspect to building them. And in this concept in 1974, as the shuttle is progressing, this was called the Conroy Virtus. And this one is fairly popular, searched on the internet. Hershey bar wing, which was theoretically easier to build and better for range. But this was a twin fuselage that was derived from B-52s and used the jet engines off of the B-52. Conroy said at the time that this would cost $12.5 million to build, which I say to that, sure. But look at that wing configuration. He's onto something here. And this theme you'll see it play out as we go. So of course, today we have the modern day version of this where it's turning another airliner into a launcher, although it's a belly launcher. This is the orbital ATK stargazer that launches the Pegasus rocket. And notice not enough space between the belly of the airplane and the ground. Because if you wanted to make more space there, you'd have to do extensive modifications to the landing gear. So let's talk about the evolution, given the history of launchers. The evolution of this concept and this design from Burt Rutan's sketches all the way up till today, the configuration that we're flying actually takes an interesting path. I was able to gather some sketches that were made, casual ideas that were just archived over the years. This is from April 1990, and it's a Burt Rutan sketch. And it's a doodle of a centrally located or centrally loaded carrier with an offset pilot. And this is the first manifestation of that offset pilot on this carrier configuration. From the conceptual layout, very beginning, Burt starts considering the experience of the launch as an attractive feature and includes an observer station in the aircraft. And in this one, you'll see there are observers in the right-hand fuselage just behind the crew. So he's from the beginning considering what that experience would be like. And again, here's another iteration of that. Notice the Spaceship One sort of configuration. Then there you can see a Spaceship One, Spaceship Two style. But look, the crew is in the right-hand side of the right-hand fuselage, and we're starting to see ideas of how to reuse very complex systems like the engines and their nacelles. So you can see the spaceship platform emerging in this design. Here's where it starts getting real. This is when more than Burt is just working on this. This is actual engineering applied to these ideas. And you start to see in this configuration, there's a 277-foot span. We're reusing 747 nacelles, but the big concept here, the big breakthrough is that this is going to start to reuse the major airline systems and components. And that is the winning combination of this idea of this configuration. Notice the crew layout in the right-hand cabin. There's an actual, Burt's putting in some thought into actually how the crew resides in that cabin to better accommodate the experience. And that persists throughout all of these. So now that we're getting into this concept, we're starting to talk contracts. We're starting to get more of this. This is August 2000. We're getting more serious, and we can tell because we've got a 3D model now. That means more people are working on it. Notice here in this configuration, minimize wetted area, but look at that landing gear. That custom landing gear wouldn't be available from any donor aircraft. It's just too tall and very clearly is going to have some cost issues. This note is from the 2000s again, or this graphic. So moving on, here's another pencil sketch that comes out. And I showed this one because I think this is a very important sketch that Bert did. It's not that Bert is simply a great aircraft designer. His approach to design is mission-centric, which it identifies ways in which he can utilize unique design to fulfill the mission. It's not uniqueness for the sake of being unique. It's uniqueness to achieve a goal. So Bert details here what he deems risky aspects of this design. The ground crew on board is in the nose. G transients for takeoff and landing and crew egress issues. He's addressing that here with the crew sitting up in the top of the vertical fin at the joint between the horizontal tail and the vertical fin. There's electrically signaled ailerons because he's already identified that the mechanical signaling through the tail and fuselage to the wings would be complicated. And this one has a crew bailout configuration that allows a flyback vehicle. So there's some interesting concepts happening here. And also the Bronco tail is really mostly for signaling runs, not necessarily for structural in this configuration. So because we're Stratolaunch and we are constantly looking for ways to advance schedule, that concept gets evolved into 6 engines, 6 747 engines. Notice the V-jet idea, which is an original scaled airplane. The tail, top of the fin, has the fuselage from a jet that was previously manufactured. So there's a money savings concept for using tooling from previous programs as the cockpit, sort of the crew station at the top of the tail. 2 Spaceship Two rocket engines for JATO type takeoff and a tapered outboard wing. And this is where the donor starts to be targeted as the 747 in a serious way. This starts to get rolled into the plans and the concept for building. So at the commitment of the contract of Stratolaunch, this is what the configuration was agreed upon. And you can tell that we've got a lot different jet now in the days past. We've got the same outboard wing taper still, as you see here. The wingtip scheme is the same. The engines are in the same place, but we didn't go with the Bronco tail. And the reason why is many trade studies showed that it actually was heavier than our 2 cruciform tail configurations that we have now. Multiple trades concluded that. And note the cockpit placement at the top of the fin. And I like this particular concept because at this point we were toying with the idea of crew egress being an emergency slide through the vertical fin and out the bottom somehow. There was some concept thrown around with that. And that's completely unusual and out of the box thinking that kind of made this advance. So as time passes and the design matures, we get to this configuration. And this was seriously traded as a configuration that would have the range and the lifting capability, but we start to see complexities with using the systems. And we start to see economic issues with a curved wing section in the center that it'll be hard to build and expensive to build. And also it is interesting to note that these are modeled basic size 747 landing gear. So you can see this is a very large aircraft. So advancing in time, here's what we called the Horseshack project. And it's a paper study that we use to bring our current configuration to finality. Kind of, you can see the adoption of the 747 forward fuselage, the reuse of the windows from the 747, the engines, their nacelles and their pylons. And we've got the high horizontal tail in a cruciform configuration. But we have 2 different mold lines for the fuselages left to right. We'll talk about that in the next one. So here we are today. This is our loft and our design outer mold line that we use to design the airplane. At this configuration, we have the launch pylon in the middle, just like all of them, but now we have identical cockpits left to right. But for systems and for the control, the pilots have always sat in the right. And that's been a carried through configuration that we've not changed or challenged the entire time. But there are also reasons for those are reuse of the 747 windows into our loft, which I've always been impressed with, that we were able to reuse the transparencies from a 747. So what is this aircraft now? How big is it? I like this 3 view because it shows we're 385 feet, 238 feet long, Max design takeoff weight is intended to be 1.3 million pounds. We haven't tested to that point yet, but we are definitely using the airplane with the intent to build up to carrying more weight eventually. The current mission is not nearly the payload that was originally anticipated for this airplane, but the system complexity is challenge enough. The mission radius was maintained at 1,000 nautical miles and a balanced field length of approximately 10,000 feet. We think that we also have the world's largest single aircraft component, which would be the wing spars, which are only partial span. They go from the dihedral brake or the planform brake to the other planform brake. And we have not been informed of any other piece bigger than this, but they are approximately 250 feet long each, the spars and the wings. So we think that's the single largest aircraft component ever built. And we'd love to hear from you if you have a challenge to that. All right, has anyone ever seen this chart? I like this chart. Someone did us a favor by making this chart. I found it on Wikipedia, and it shows this Model 351 Stratolaunch overlaid over a 747, and at the same time, the Hercules H4, Hughes H4 Hercules. We have the H4 Hercules by 65 feet, incidentally, a number that I don't ever forget. Here's a look inside the Stratolaunch aircraft as it is now, and you can ignore that payload in the middle. I grabbed this drawing because this really does show what our system's complexity looks like. There are 4 hydraulic systems, almost a quarter statute mile of control cable. Each engine has an air-driven hydraulic pump, an engine-driven hydraulic pump, and an electrically driven hydraulic pump, together making more than 200 total horsepower of hydraulic service to the flight controls, the landing gear, and the braking systems. Each engine provides electrical power, and they pump it into 2 massive power bus systems that meet at the center wing. No, it is not possible to access the fuselage or convey through the wing while in flight. The pilots are sequestered only to the pressure vessel of the right forward cabin and are unable to actually transfer into the fuselage while in flight. But that said, you cannot walk through the wing either. The wing is only about 5 feet thick. It is important to note that the access to the structure on this aircraft is unusual in that it's gained through very many person-sized access holes, allowing inspection of virtually every structural element of this aircraft. I like to call this crazy access in the world's largest airplane. Never has there been an airplane I've worked on that we had this kind of structural access. Definitely a benefit. Here's the cabin layout, and it's pretty simple. It follows the basic 747 layout with a pilot, co-pilot, and a flight engineer, and other stuff monitoring other stuff. We call that airplane stuff. We call that rocket stuff. Literally, these are the support systems for the payload and the experiments that can happen on board. We have an optional seat for a flight test engineer observer. We haven't put that in. It's just kind of close to the door. And of course, we tried to build a lab for the pilots. Sorry about that. We just ran out of time. So instead, we got a travel John. So where were these airplanes originated from? Parts birds. We bought 2 747s, lightly used and in good condition. We wish they were from Craigslist. We like to say they were, but they were a little bit more legit than that. We accepted the airplanes in flying condition, and the day they rolled in, had a company meeting on board. It was very intimidating because we stood there looking at the airplanes, wondering, knowing we have no business harvesting the systems out of these massive airplanes and putting them in something so big. Having been, White Knight 2 having been the largest aircraft any of us had ever built. Of course, we took many of the flight deck components, and in the end, this is what our parts bird looks like before they get hauled to the boneyard. No engines, very few systems, and minimal landing gear to transport it. The 747s donated their entire cockpit floors, controls, seat rails, instrument panels, and they eventually became the simulator, the cockpit floor in both cabins, left and right. We used the same yokes and rudder pedals from those harvests. And these are how the donor airplanes were, their fate. They were sent to the boneyard and reduced, as they say. Only one exists today, and the other one is basically gone. So I like to go through 4 basic tenets of building Stratolaunch, and this is an effort to show kind of the basic philosophy that we had while we were on this massive, overwhelming project. Number 1, keep the requirements focused. This elevator goes to this horizontal stabilizer. That day, we mounted these 2 and set the hinge line. Simple, clear requirements. Build flat parts when you can. Curved parts are hard and take tools and take time and expense. Flat parts, you can make them over and over again on the same table. So that kind of explains why the fuselage sides are mostly flat. Use garage tech whenever possible. This is one of my favorite images because when tools need modification, they need modification right away, and we don't like to wait on new tools. And what good is a brand new rivet gun in the tool crib if it has the wrong configuration? Make it the right configuration and get the job done. Notice the pedal actuating a rivet gun with a string that's duct taped to the floor. One of my favorite modifications of tools. The third of 4 tenets, don't reinvent the wheel, especially if you can buy one. Here's the 6, actually in this picture, we have the 6 main landing gear doing a brake system check, and the entire brake system, hydraulic system was laid out on these tables and tested as a functional test before they went into the aircraft. And if you must invent, don't forget rules number 1, 2, and 3. In this photo, you see a spar cap that was over 250 feet long, part of what we think are the largest aircraft parts ever made. It was very long and floppy. It was nearly impossible to flip upside down. So someone smart came up with a machined foam wheel that had facets that we could just roll it across the floor and work on any side of the spar cap that we needed without putting undue torsion on the part itself. Pretty great idea. So those are the 4 tenets of keep it simple. So let's talk about the assembly of this. I'm a model airplaner and I look at it from that point of view. We put this airplane together just like a model. That part goes there. Pretty simple. And it was a daily occurrence to see huge parts go in place. In this picture, you'll see the tail section, the entire tail section, vertical and horizontal, put together as an assembly first on the floor, and then as one giant assembly moved into place in a very impressive lift. ×2. We did this twice, once for each tail. Just for scale, I love this picture. Looking down, we actually had a drone in the hangar this day, and this just shows a couple of people standing there for scale, and walking on the wing was a routine, everyday way of life, and it became so routine that we often forgot that we were walking on an aircraft structure. Also, when you adopt systems from well-used airliners like 747s, reusing the engines and nacelles means you get to use the commonly available hoists and engine lift hardware for the installation and removal. But oh wait, the 747 has dihedral, and these hoists needed modification to make that work. So oops, you learn as you go in this game, and that was one of the fun lessons that that I was most admirable of in how they adapted to the lack of dihedral in our installation. And they still use those engine hoists to this day. Also, simulating this airplane is a big challenge. It started off as first a basic sim in the hangar, and we made it bigger by trying to add in the instrument panel and the other cockpit elements. And today we now have settled on a fixed base simulator inside of a hemispherical projection dome. And it works remarkably well. And it's so interesting how the brain and the ears just seem to feel like you're flying in that. The systems are quite well represented in our simulator, and it is used all the time for pilot training, proficiency, and also proficiency in our control room. We also have some fun at Stratolaunch, and I like to show these slides. I feel like we were in with the cool kids when we were building this airplane. We got visits from Wally, as you can tell, and people from Disney. It happened quite a bit. And at times we had fun. Here's the day the chief engineer showed back up from vacation to his office filled with balloons. Let's talk about the hardest parts of building this airplane. And this is the last part of my presentation. The wing was built thin for range and straight for cost. And the biggest challenge of this airplane was the wing root and the design of that wing root. The maximum bending moment is equivalent to 1 elephant mile. If you know the concept of foot-pounds and torque, the elephant mile is a massive amount of torque, and that's an adult African male elephant, by the way. We had to qualify that once. Also, some of the hardest parts is understanding how this airplane is different from others. It's what makes this job interesting. And on the first rollout shown here, we were very concerned with skin temperature from solar heating. So we placed tattletale thermometers all over the airplane in this picture, and that experiment happened just on the rollout of the aircraft. Another hard part of building this airplane is moving the airplane. This was set up as kind of a joke, but it is actually something we talked about, moving the airplane by using a crew of people with a rope. It was floated. Accessing the airplane. I like to show this picture because it shows I actually took this picture from the other tail, and I'm up in the high scissor lift there. It was actually hard to find scissor lifts that would reach the top of our tail. And when we did, we had to get the ones that went really high. So there was this confronting of fear of heights. And I actually went through that on this program. I went from hardly being able to climb up a ladder to being able to ride the scissor lift up on a daily basis. Also, that isn't to diminish what the real hard part was, which is our system complexity. As an image of our thrust levers and just showing that there's 6 engines to manage, and we tried our best to simplify this design as much as we could. Also, there's a non-aviation related portion of the hardest parts, and that's growing the company and managing the project. This is our company as we started. That kind of shows the evolution of how big this company got to support an airplane like this. And at the bottom, you're seeing over 350 people working on an unfinished Stratolaunch. And then, of course, we had to develop an entirely new body of technology and use that body of technology concurrently while we built. In the image on the left, those pins are 4 inches in diameter, and that is a shear load test for one of our wing sections. Probably, I think that's a shear panel, actually. And at the bottom, you'll see the semi-truck trailer that was used just to move the wing test article. So designing the systems for which we build things became part of this project and really took on a life of itself. And of course, the big emotional paycheck. It happens that every day we live in a life of being constantly behind schedule and needing to make many, many decisions every day, but there has to be an emotional payoff. And very clearly and very distinctly, first flight was that day. 2.5 hours of flying, 17,000 feet, and one fantastic landing at the very end. And truly, this is, in conclusion, this is the payoff, and this is the why we do this. I get to work with my best friends in this job, and every single day it doesn't feel like a job. It is an experience. And I just like to show this image because I have this hanging on my wall in my house. This is a very truly emotional paycheck for me. So what's next for Stratolaunch? I'm just going to touch on it. We thought we were done building the airplane. We're not. There's still plenty more to go. More systems expansion, capability testing. We got plenty of ground test ahead of us as we implement a launch pylon and a hypersonic payload. We've got plenty of flight tests associated with that. And then in the end, we're going to launch a fast rocket. And that is going to be one fantastic day. And what does that rocket look like? Well, this is our Talon A. It's a hypersonic test bed. It's unmanned and autonomous, and it will be a Mach 6 vehicle with flexible. The idea is that it has flexible payload configurations with a stepped integration plan. We'll be able to, you can see on the bottom right, there's some dots that are pointing out the areas in which we can place payloads, sensors, and other experiments for instrumentation. Probably the most important thing about this system is that it is reliable and it's repeatable, but most importantly is it's retrievable. This is a retrievable vehicle that will someday autonomously land. And this is what the mission is, the basic view of what the mission looks like. This is my last slide. And I just want to say that this is just getting started. This really does demand an entire presentation of its own, but this is a basic overview of what our hypersonic mission is. And so with that, that is my last slide, and I am ready to hand over to Colonel Evan Thomas. And just excuse us for just a minute while we switch seats. Oh, expand that to dots, yeah. Start menu and okay, very good. All right, well, thank you to Mason and Zach for those intros, and I will press on then with the second part of this, which is more to talk the flying lessons from the first flight and the second flight. And just want to confirm you all are seeing the title screen, right?
Yes.
Thank you. All right, so I'll briefly cover, talk a little, Mason gave a great intro on the carrier aircraft itself. I'll be talking about the first flight profile development and some of the things we went through to confirm to ourselves, is the jet ready to fly? And were we ready to fly? And then talking about some of the known unknowns of a first flight, and then some of the results and innovations. So Mason already did a really good job describing the overall size of the airplane, obviously very large. This is the same slide he showed. There are two things I'd like to highlight on it. One, as he said, the crew is over in the right-hand fuselage only. So we're right up there, fairly cantilevered out in front. And then the second thing is, if you look at the airplane where its weight is, the fuel tanks are all outboard of the fuselages in the wing. There are no fuel tanks in the fuselages. They are basically hollow tubes. So if you wanted a physical analogy, it's a bit like a shopping cart with a heavy barbell strapped to the top. So it's got a lot of inertia and weight out in the wings, and that's going to come into play later on the flight. In terms of flight controls, I'll go over this a little more detail. For the first flight, all of our flight controls were mechanically signaled via cables. So cables running from that right cabin all the way out to both empennages, all the four elevators, the four rudders, both banks of outboard, or both banks of ailerons on both sides. So a lot of cable. All the flight controls, of course, for an aircraft this size, hydraulically actuated and irreversible. And as a review, we have basically 2 elevators and 2 rudders per fuselage, and then 2 banks of ailerons on either wing. So the first flight really had one objective, like all first flights, and that was to land safely. We had a bunch of other sub-objectives, but really that was the main objective. The risks we looked at for the first flight, the primary one was landing this airplane quite wide on the runway. So runway departure on the landing was a big concern, but also how was the airplane going to fly for real? So inadequate stability and control,
the possibility of getting pilot-induced oscillations. And then also, it's a very large carbon structure, so the possibilities of getting some odd structural vibrations, biomechanical feedback between us and the aircraft and the control inputs, and then pilot perceptual concerns of sitting there out on the right fuselage way out in front. Ultimately, the first flight was about, can we precisely control the aircraft to a stable, centered landing? So going again on that big landing challenge, we got a 200-foot wide runway here at Mojave, and it is 114 feet from the outside of one set of main landing gear to the outside of the other set. So this, we're pretty wide there, gave us about 43 feet to either side to play with. Again, we're a bit like a shopping cart, 2 nose gears up in front, and then inline main landing gear, 3 trucks worth of for 6 tires on each line there. And then also we come into the flare a bit nose down, sort of like a B-52. So that concern was such that we didn't want to land nose gear first and start porpoising, not only porpoising fore and aft, but potentially side to side as well. That would be a bad thing. To give you another sense of perspective, the picture that's shown here was taken from space while we were out on the runway. Okay, I was going to talk a little bit about the our buildup in taxi testing, but I think I will just, in case there are any questions about that later on, we can double back to this slide. Needless to say, the taxi test program for this airplane was not just, let's take it out a few days prior and run it down the taxiway. It was a fairly long and involved process. Okay, so it came time now to think about this first flight and what we wanted to do. So we started with handling quality evaluation basics, which is 4 primary steps. First, you want to do thorough ground tests so that you understand your system, the flight control system. Next, you want to, when you're airborne, you want to do some open loop responses, see what the aircraft's natural response is to inputs, and some basic capture tasks, bringing the pilot into the loop. Then you want to build up to doing high gain, sort of intense, quick, rapid inputs to do a stress test. And that's where we're looking for what we call a handling qualities cliff, or any sudden degradation that would be very bad to learn about right during the landing. So we want to look at it up and away at altitude. And finally, you would normally assess the handling qualities and workload for mission suitability. On a first flight, we did not care about that. So that one was off the table. So this essentially led to we started out with a basic profile. We're going to climb to 15,000 feet, nice comfortable altitude, 150 knots. We're going to, we take off with the flaps up. We're going to do pitch, roll, and yaw maneuvers to check the handling qualities. We're not going to do anything high gain, flaps up. Then we're going to put the flaps down, which was a significant test point to get done. The flaps, by the way, have 2 settings, up and full down, which is 70 degrees down. So the flaps act as flaps, but they also act as speed brakes, essentially. Once the flaps were down, then we were going to do our simulated landing stress test. Typically, you would use that with your chase aircraft as a target out in front of you, and then descent and landing. As we started thinking about, well, how exactly we're going to do this, it became rapidly obvious that this was going to be an iterative approach. So we have our that standard approach, but there are a lot of unknowns here, and one of them is our air data system. Is it in any way accurate? We sort of need to know that before we come back to land. So the first thing we needed to do is, all right, well, we need to add some pacer checks in here to check the pitot statics and look at our predictions. How is our AOA prediction, our coefficient of lift, our trim elevator settings? So we want to look at those, both flaps up and flaps down. Then next up, we said, well, if we have a problem early in the flight or in the flight, we want to get back on the ground quickly. We want to get the flaps down. But before we put the flaps down, we want to make sure we have enough roll authority in case we have an asymmetric flap or some sort of problem with the flaps. So that meant we had to put right up in front, all right, we'll do our pacer check, but then we need to go check our roll authority and our roll handling qualities. So no problem, we'll just rearrange the plan and put that in place. Well, then when we started looking at doing these roll maneuvers, the roll authority maneuvers, where we're essentially doing them both feet on the floor and with some coordination, we realized there was a potential to build side slip there, which we had not looked at before. And doing an open loop side slip maneuver was not a safe or a smart buildup. So we'll add in a flaps up, wings level side slip to go out and take the airplane to the maximum side slip that we predict we'll see in the roll handling qualities. And then we'll do our roll authority check, and then we'll do our handling quality check, and then we'll get the flaps down. So you can see how this profile slowly built over time. And then after we were flaps down, we realized, well, we needed to do a build down, a controllability check essentially from flaps down speed, and just work our way down at the control room's pace to a landing speed, again, to check out controllability and our predictions. So that came in. And then the next thing was, well, how do we add a little more stress to this stress test or make it harder, more like the actual landing? And that was, we said, all right, well, I used to work with a guy who always said, when we're looking at handling qualities, if something's worth looking at once, it's worth looking at 3 times. So we upped the number of simulated landings we were doing at altitude. We threw in a side slip component during those simulated approaches. We got rid of the idea of doing this off of chase because we're just far too big and it was a little too scary for all of us. And we also added in some planned low approach, one low approach with the option to do other low approaches prior to the landing. So that's what the essentials of the first flight looked like. We drew some lessons from that process. Number 1, on a first flight, everything's an unknown. And the lesson 2 from the aircrew side, we said, follow your instincts. What scares us the most is what we want to look at. So if we back up to those handling quality evaluation basics, and we're going to talk about a little more about the thorough ground test and building this up. But before I do that, I want to just touch very quickly on how do you evaluate handling qualities. I'm pretty sure if we had a car out in the parking lot, and we handed you the keys and said, go tell me if this is a good driving car or not. If you ask that to 20 people, you will get 20 different opinions. So the challenge of how do you standardize qualitative comments and avoid design by opinion was a major problem throughout flight test and aircraft development, really until the 60s. It started getting much more scientific, and the advent of the Cooper-Harper Handling Qualities Rating Scale, which relies on a very tightly defined task, which is repeatable, and the pilots can train to, so that you take variation out of the loop there. And then you set desired and adequate criteria. And then you execute the task, and then you grade it against this scale, and typically end up with 3 levels of rating. One is satisfactory without improvement. The plane's good for the mission. It's adequate with a tolerable workload. So it's okay, but it could be a lot better. And then the level 3 is, well, it's controllable, but you really can't do a mission with it. So with that background, we'll go back to that thorough ground test. As we completed the build on the airplane, which, as Mason said, was quite a task, we discovered that the pitch, breakout, and friction forces were significantly higher than the design point was, and certainly higher than any of the previous hangar or bench testing had revealed. In fact, in terms of comparing it with mill standard specifications, which break out, different breakout or friction forces into level 1, 2, and 3, we were above level 3. And it turns out we were pretty much up there with roll and yaw as well. Which brought up 2 questions. How valid are these mill standard specs? Because they are very oriented towards high performance fighter and trainer aircraft, not really a large lumbering transport. So that was one question, but the bigger question was, is this airplane acceptable to fly, or do we need to do some redesign? So now it's time to go back to that simulator that Mason talked about and find out, is this jet ready to fly? So our objective was to evaluate the as-built flight controls for the first flight. Our handling qualities task was very simple, straight in landings. We didn't need to do any fancy offsets or anything like that. This airplane's handling qualities are difficult enough that a straight in was it. And we had a performance criteria fairly straightforward, our pitch attitude at touchdown, because we were focused on pitch at the time. Our results were not great. We had Cooper Harper 6 was our average, so we're borderline level 2 into level 3. We also saw a number of pilot-induced oscillations, non-divergent pitch PIOs. The flare workload was very high, focused on pitch, and we assessed that we had no margin to cope in a higher gain environment, which is what we'd see in the real world versus the sim. Looking at a few traces of what this looked like. So on these traces, time is on the horizontal scale. If you look at the second set of data here, that's pitch inceptor or yoke forces. The orange one that's noted as pitch friction band. You can see in there, there's a lot of sawtoothing and back and forth. That is the pilot going back and forth across this friction band. Basically, you know, every time you reverse the direction, you have to push across the friction band before you get an elevator response. And also due to a number of things, the signaling delay through the cables and all that, and the actuator is actually quite low, but the inertia of the airplane tended to lead to this delayed response. And we see here the pilot getting out of phase between pitch yoke inputs and the pitch attitude response of the airplane. Taking a look at another example of this, where we were coming in fairly fast, which was the proposed approach speed. Here you can see in this case, the pilot is essentially PIOing for quite a while between either going to hit nose first or just barely hit the vanes first, so that the airplane is level and pitching nose down, nose up, out of phase. So clearly this would not be a condition we would want to land with. So out of all this, one, handling quality simulation was very important for this flight readiness decision. We knew we had to do something different, but now the question is, well, how good is good enough? So we decided to relook at those tasks. We wanted to give ourselves tasks where we were happy we had adequate control plus some margin for what this would look like in the real world, and sufficiently tasking to expose deficiencies in the simulator. Landing was the critical task, but we also added in some up and away single axis high gain tasks as part of a stress test. We also picked 3 primary criteria to go after. One was runway lateral error, clearly a concern when if you only have 43 feet to work with to either side, you don't want to be landing 30 feet off to the side. Having a positive pitch attitude, so we didn't touch down nose gear first. And then how well we aligned the fuselage with the runway. This aircraft, because of the inline nature of those main landing gear, we want to land with the fuselage aligned with the runway using a wing low approach as opposed to a crabbed landing. So the simulator prior to this had really been envisioned as a training only simulator, not necessarily a handling qualities evaluation simulator. So we had to dive in and look at a lot of the assumptions, looking at how well we could generate environmental conditions, doing a precise measurement of the aircraft's flight control system and mimicking that in the sim, looking at ground effect, other aero effects, the actuator dynamics, the simulator visual. So a sort of corollary lesson from this was, yep, everything's unknown, but you need to challenge assumptions and models everywhere where you can. So the result of this problem was we went back in and did a significant breakout and friction reduction engineering effort. It's a huge engineering push. The shop folks basically tore out the flight control system and reinstalled it twice, I believe. So that was one set of this to reduce those numbers. But then we also challenged the approach and landing speed assumptions, which were built on FAR certification standards. But we're not trying to certify this airplane or demonstrate certification. We're trying to land it. And it turns out the one size fits all numbers that were in the FAR were not well suited for our aircraft. So we revised our approach and V-reference speeds. After all that, we went back in the sim. Handling qualities were now acceptable for flight. They were level 2. We felt we had some margin. To give ourselves a little more margin, we'd originally planned to fly with 10 knot crosswind limit. We lowered that to 8. But the best thing was we were able to make all these decisions backed by solid qualitative and quantitative data. We all like data. So this is what it looked like once we made our changes. Again, time is on the horizontal axis. If you look at the second set of traces here, you'll see we still have a little bit of back and forth with our yoke force in pitch, but with the pitch friction reduced, we're not seeing as much sawtoothing. We still have the underlying lag between pitch input and pitch attitude response. However, the PIO is suppressed. We're not seeing nearly as detrimental effects. And we also said, oh, let's add in some realistic gusts. So down at the bottom here in the blue oval there, you can see on this run, the pilot was dealing with a crosswind gust right coming into the flare there and having to work to align the airplane while doing the pitch flare as well. In terms of some touchdown scatter plots, so each little dot is represents a spot on the runway. The horizontal axis is the crab angle, so the difference between the fuselage and the runway heading. And then the vertical axis is pitch attitude. And you can see before friction reduction, we had a lot of landings down near 0 deck angle or even nose first. Whereas after the friction reduction, our grouping is much tighter. We're consistently up in the 1.5 to 3 degree range, and our crab angle is better controlled. Likewise, if we look at lateral offset versus distance, on the left, we see before friction reduction, we've got some landings which are on the runway edge, and the grouping is really in the 20 to 25 foot zone. Whereas on the right, after we did our friction reduction, now we're consistently down below 15 feet with the biggest outlier to 20 feet. Far more comfortable going into first flight with those results. So our takeaways: specs are a valuable reference, even on a unique aircraft, but you've got to know that the history of that specification and what its handling quality implications are. You cannot just blindly apply it. And also, even on a big, strange airplane like this, the classic tools of handling quality evaluation work extremely well. You link them to mission requirements, add stress when sitting in the sim may not necessarily be as stressful as the real airplane. Use simple, well-defined tasks, and make sure you have a diversity of multiple pilots. The last thing you want to do is have one pilot, no matter how good they are, go in and say, yep, that's great, because they may not see it the way other pilots do. All right, so let's talk just for a moment about that narrow margin, because that always sounds scary. We did some extra things to try to improve that margin by making each landing a little bit different. So we're able to go into the sim and change aero coefficients and inertia, moments of inertia, control power, and do lots of landings with variations in there. We also went and got a surrogate aircraft, the Calspan variable stability Learjet. We modeled the Stratolaunch feel system in there and went out and did touch and goes in their airplane. And that was really great training. And those in-flight rehearsals of the mission flight profile just helped us keep sharp on our handling quality observation skills. So here's a video of us on approach on the first flight. I am trying to be as low gain as possible here. Oh, sorry, let me go back there. I'm trying to be as low gain as possible. I'm trying to put in as few inputs as possible. I still see that I'm putting in quite a few inputs for what should be a nice stabilized approach. So the question of whether we were ready, going out and doing those Calspan Learjet flights taught us some valuable lessons. One was we were going to have the pilot monitoring, the pilot not flying, run the throttles and control the airspeed to reduce the pilot flying's workload. We would both do handling qualities up and away to get 2 different opinions. And we added some standard operating procedure decision points and callouts. We also had a full mission control room, and we did simulators with us in the sim and the control room being fed information from the sim. Not only was that to prepare the control room team, but it also taught us that there was an advantage of equipping Chase with an ability to hear the hot mic comms between the control room and ourselves. We planned out spots in the profile to take a breath and pause and think and communicate. And just the pure value of having someone on that team who is training and thinking up disasters to throw at the team was very valuable. All right, some of the known unknowns. It's a very large, heavy composite airplane. You could come up with things that could happen all day. We were quite concerned about a number of these, probably aeroservo elastic issues and being shaken in the cockpit, and that getting into the controls was the most significant one. So we focused on that. We pushed hard for an ASC analysis, and that analysis basically bounded some of the accelerations we expected to see in the cabin, and that helped make that a predicted unknown for us. Another big known unknown was cabin kinematics. I mean, again, there we are, we're out to the right, we're out in front, and there's always been a lot of concern about, well, in a dual fuselage airplane, as we roll, are we going to see an NZ, up and down G effect from rolling? And what's going to happen when we're trying to land? And if we roll and we suddenly feel a G increase or decrease, is that going to make us pitch? Which was a concern. But we actually went out and learned a lesson before we flew, and that was to discover that answer was already available. If you remember that cool dual fuselage C5 that Mason showed you, that design had been flown in a variable stability aircraft, the Calspan TIFs, by pilots in the air. And we were able to look at that report, the NASA report, and see that for a comparable roll mode time constant that we had, and roll rates, they had seen negligible pitch impacts during flare to land from this effect of being off to the side. So that was a huge confidence builder. So finally, we got up in the air, April 2019, and it is cliche to say it went like our simulator, but it really did. It was very impressive. The pitch handling qualities were better than expected. The roll handling qualities were pretty much as predicted. We had a very long period, flat Dutch roll. The airplane just yaws side to side very slowly. However, we did find that we had a larger than predicted yaw due to roll. So I'll show you here. I'll run the video on the left first, which is our view right outside the pilot's window. And it should be some commentary. Caution is for a false yield indication.
More than expected.
So right there at the end, I was saying we're getting a lot more side slip in the turn than expected, and my co-pilot Duff said, "Yep." So if we look at that same turn from a camera back on the tail and watch the ridge line out in front of us. So here we're pretty much just on takeoff leg, and we're just starting the roll. And you'll be able to see that as we get into the just slight bank angle, you can see a lot of yaw rate develop as that side slip effect is kicking in. So we had this larger than predicted yaw due to roll. After the flight, we realized our yawing moment coefficient due to roll rate was significantly different, significantly larger than predicted. It's normally negligible in most airplanes. It is not negligible in our airplane. And the second big thing was landing flare perception. We talked about the roll and pitch. What we didn't realize was that a slow yaw rate with us way out in front was going to seem like we were getting pushed sideways rather than yawing. And the reason that was an issue is because if you're in a wing low approach and you're getting pushed to the left, you're going to bank to the right to correct it. But when we would bank to the right, that would increase the yaw rate to the left, which would make us feel like we were moving further left, which would make us bank right more. And here's a view from the center wing. So this is a camera mounted right in the center wing. Oh. Back that up. Of the landing. This is the first flight landing. So you can see the bank going in there for the crosswind we had coming from the right-hand side. And we've got slow yaw rate to the left going on as we touch down. The in-cockpit video, I think I'll skip this one. It's just a continuation of the last one, just in the interest of time. And then this one's always fun to watch, the belly camera video. You can see all the people who came out and were parked there short of the runway for first flight. But it gives you an idea of the size of Stratolaunch coming into land. And mains and front touchdown. All right, so some of our innovations that helped us on first flight, we had hot mic between the crew and the control room in both directions, and then hot mic reception in the chase aircraft, so they were able to completely keep up with what we were doing with the test cards. We'd adapted AOA indexers to be pitch attitude indexers to ensure that we would not touch down nose first. Had dual band and dual path telemetry for redundancy. That'll help out later with our hypersonic mission. We did not pressurize the fuselage on the first flight. And in fact, we ended up going with a fabric cabin door, which sounded crazy when the engineer first proposed it, but it actually worked great. And then Mason showed that picture of the complex throttles. We actually used a wooden block to help keep those aligned in flight. And of course, the biggest innovation was designing, building, and testing, and then flying a 385-foot wingspan composite complex 6-engine airplane. Our second flight, our objective, it had been 2 years since we flew previously, so we wanted to land safely again, and hopefully have a better landing. But we'd also made some changes. First, we had changed the outboard aileron control system. We added a yaw augmentation system, added a runway alignment display for the landing, and then we wanted to go out and test our flutter instrumentation and techniques. Our risks, we still had that runway departure on landing, but some of those other risks were now knowns and not present, so we could take them off the table. So the two biggest changes in the flight controls, the outboard ailerons, we essentially snipped the cables and turned those into command by wire with a direct control law from the yokes, and then added a yaw augmentation system in parallel with the mechanical yaw signals. We also converted all this purely steel cable loops into hybrid steel and carbon configuration. So our second flight results, all systems again perform very well, as complex as they are. It really is amazing that we've got 2 flights on this airplane with virtually no significant write-ups for maintenance. The outboard aileron functionality worked perfectly throughout the flight. We actually went ahead and turned them off and evaluated the handling qualities in that failure condition, and that all went well. We got our flutter assessment in, that was successful. We had a better lineup with the runway alignment device and a better landing, which made me very happy. And here's the video of that the second landing, a little bit longer on the lineup. So as you watch this video, you can see the underlying very slow yaw. It's really only a half a degree to a degree, but it's very hard for the pilots to suppress that and stop it. It's almost imperceptible actually in the cabin. And you can see the bank is changing as I'm trying to adjust the lateral error as we come into the runway and make those fine corrections. And everything's looking pretty good here on the lineup. Again, we're banked slightly to the right for the crosswind coming to the right. And we have a nice touchdown, airplane's rolling pretty straight. And then as we get on the brakes are quite powerful. The differential brakes are very good for steering, but because they're strong, we tend to get a little bit of wiggling as we come on the brakes. And that's what you see right there. All right, I think we probably run a few minutes over, but that is the conclusion of my portion. And I think if we can open up the floor for questions, or Ken, whatever you'd like to do next.
Yeah, wonderful presentation. I think there's a question in the Q&A box, but I think that was for the previous, for Mason. So, Zach, do you want to?
Mason's here now, so
okay.
Is this the question about the ACO or FSDO?
That's right.
Yeah, yeah. So for the first flight, the aircraft, it was the MIDO who actually, since it was a first build of the airplane, was responsible for the airworthiness. And since then, we now fall under the Van Nuys FSDO for the continued airworthiness and working with them.
Great. Mr. Santosh Kumar raised hand. So, Mr. Kumar, go ahead.
Awesome presentation. I actually got to tour with SFTE Stratolaunch the Rock, I guess was the actual name of it, being built back around 2014 or so. It's awesome to see how far you guys come from it being just a black composite thing from which you couldn't even tell from one end to the other because it was so large. The question that I have for you guys is the parallax from a pilot perspective when you come into land. Are you guys basically, treating it like when you guys land in the military with the tactical jet that you're landing on like one half on like the right side of the runway, or on one half of the runway, as if it were like two different runways from the perspective of the pilot? Or how does that parallax affect the vision perspective from when you guys line up to land to ensure that you guys are on center line between the two fuselages?
Yeah, well, interestingly enough, it seems very weird, but when we're flying it, there are times, unless you look over to look at the other fuselage, you don't actually realize that other fuselage is there. So the lineup is fairly conventional. We do have a stripe painted on the right side of the runway at Mojave that we are using to line up in the center of that right-hand side. So that is what we're queuing off of. You don't want to look at the center line. You don't ever want to go towards the center line because if we end up on the center line, that means the left fuselage is in the dirt. So unlike, that's a thing we had to unlearn, is never go towards the center line in this airplane. But in terms of parallax, not really an issue. Our largest perceptual problem was the one I talked about, where the slow yaw rate is perceived as a lateral push to one side or the other. And that's where we came up with this runway alignment device, which is really fairly simple. It's just a set of lights to either side up in the pilot's vision that gives us cues if we're starting to get off heading to one side or another.
would that be similar to like a drift indicator? I don't know if you remember years ago at SCTP, they had a similar type thing for brownout conditions for the MV-22 Osprey coming into land in brownouts. They'd have like a drift indicator on the instrument panel to indicate which direction they're drifting, so you can control inputs when they're completely blind, or is it something along those lines?
Without remembering what that specific system was, but yeah, it's essentially a heads-up, simple indication of the difference between our heading and the runway heading, so that it's up in the pilot's view. They don't need to come down and cross-check anything.
Awesome, thank you.
I think Maryland McPullen, you're asking us, do we have a third flight planned and when? Yes, we actually have a whole series of flights planned, and the goal, again, COVID caveat, but the goal is to get off a third flight by the end of this year. We'll be focused on our gear, so it should be a pretty exciting flight.
Wonderful. Thank you for answering.
Yep.
And awesome presentation, by the way. It really was just fascinating. I've been following your progress for a few years now, and it's just fascinating to hear the whole story. So I'll continue to follow you, and good luck.
Thank you very much. Looks like we have a question regarding hypersonic weapons testing. Yeah, let me just clarify that real quick. We're not actually testing hypersonic weapons ourselves. We're just we're really testing technologies in the hypersonic in-flight environment. So we have our Talon vehicle that we fly above Mach 5, and we test a variety of sensors and optics and materials and a variety of other items that folks are interested in testing, but we are not building a weapon system ourselves. And then, do we have a plan to integrate other systems and a standard mechanical interface? Yes, we do have for us at least, it's standard. I don't know that it's for others. It's not. Our pylon is adaptable, where we could put on actually, Mason, why don't you talk about that? Our ability to use different ejector racks with our pylons and other ideas like that.
Yeah, sure. I'd be happy to address that. Our pylon is going to be adaptable to multiple payloads, but remain being the same system. And what that means is that we can attach vehicles by different locations because we're individually separating from them, similar to what you might see in a stage separation system for a rocket or other separation systems there. So what that means is we're doing multiple point attachments with multiple simultaneous released points.
Thanks, Mason. Dale Hoffman?
Yes, can you hear me?
Yes, thank you.
Let's see. I'm a flight controls engineer that goes all the way back to the X-15 and the Minneapolis Honeywell fly-by-wire system. Would your prediction be that I understand for reliability purposes is why you had all the mechanical direct control, if I understood it correctly, but do you envision going to a full fly-by-wire system after it's checked out and everything?
Mason, you want, or Ivan, you all want to start?
Yeah. Well, certainly, if you look at this airplane, you could say, well, it would benefit from a full fly-by-wire system, just because that gives you the ability to tailor some of the handling qualities.
Right.
However, and this is a giant however, as I'm sure you're aware, to do a fly-by-wire system, you have to have a very good model of your airplane. And this is a difficult airplane to model just because of its structure and size and inertias. And then you have to have an ability to iterate that design and do a lot of flight tests to check out all the corners and tweak gains and make changes. And for that reason, I would say we don't currently envision doing that. Sure, it would be great to have the opportunity to maybe tweak and improve the handling qualities here and there. But the cost downside of that in terms of schedule, complexity that this would add, and the modeling effort, really for us, it's not worth the mission benefit to go in there and try to do that. The current system, like I said, I mean, it works, it's satisfactory.
You're 2 for 2.
We're 2 for 2, and the second one was better than the first. So we felt pretty good about being able to make a correction, and the ability of our training regimen to prepare us for landings.
Do I get a second comment?
Yes, sir, Mr. Hoffman, it's a pleasure to have you watching tonight with your history. I very much respect where you've come from. As the mechanical engineer working through the flight control system, we enjoy a major innovation with this system, and that is that we've very well solved the coefficient of thermal expansion issue. So the 747 is plagued by that because it's an aluminum aircraft with steel cables. But we have a similar but opposite thermal situation where we have a composite aircraft with steel cables. The innovation was integrating the long straight cable runs with carbon fiber portions and what we call tuning our system. And that is basically making it insensitive to thermal change. And that innovation within this design is what enabled us to maintain that mechanical system throughout. We thought we were hitting the limits of a mechanical system by distance, but we saw the signal remain intact and not lag. And then we saw that thermal issue be solved with the integration of carbon cable segments, carbon fiber cable segments. And that alone is what enabled the simplicity of that innovation is what enabled us to maintain our confidence in this system as it stands. So the advantage of going full fly-by-wire now and taking out that mechanical system is kind of it's now into the comfort zone issues.
Yep.
Thank you.
Let's see, just a point. My son worked on the MGSE, putting together all of the stuff as they were fabbing it. Doug Hoffman, did you know him, Mason?
Yes, I do. Yes. Shout out to Doug. We definitely enjoyed working with Doug. Yeah, thank you.
Sure, thank you guys.
Oh, Dr. Krevor, I just want to recognize Mr. Dale Hoffman. He's actually our AIAA member with 60 years of membership. So it's really amazing. So congratulations, Mr. Hoffman.
Thank you.
Yeah, that's fantastic. Maybe another time we'd love to hear a little bit more about X-15.
Well, you started, can you still hear me?
Yes.
You left off the first carrier aircraft, which was the B-52.
Sure. Fair enough. All right, I think we have 3 questions now in the queue. I think Santosh up again, and then Jacob, and then our very own Cooper Parrish. So
I have a historical question. Is it true way back when this thing started that SpaceX actually was the original customer for which their Falcon whatever rockets were originally going to go under this thing until Elon Musk decided to not go for a horizontal air launch, but switched to a vertical launch model. And that's when ATK Orbital became the next, I guess, proposed customer to launch their rockets before the hypersonic thing.
it is true that there was a collaboration going on between Stratolaunch and SpaceX. I'm not going to comment, or we're not going to comment on the reasons it didn't work out. But they did evaluate it, and then there was a decision not to move forward. And then, yes, that's when the pivot to Orbital, at the time, Orbital ATK, now Northrop, and the Thunderbolt was made for this aircraft.
Thank you.
Yeah. Let's see, Jacob Plateau has
Yeah,
Question.
Plato.
Oh, Plato, there you go. Go right ahead.
Yeah, I'm actually a college student at Rochester Institute of Technology, studying mechanical engineering. And I was just curious if during construction, were there any problems with weight balance with the systems being in the right-hand side? Did you have to balance that, adding any weight to the left fuselage?
Good question.
Yeah, I'll take that one, Jacob. Thanks for the question. There weren't issues, as I would call them issues, but there were decisions made about how we distributed the major masses of weight in the aircraft. And for instance, we traded things. So we have the right-hand fuselage, or the right-hand cabin is occupied with a lot of systems and flight crew. So we, for example, put the APU in the left-hand fuselage in a strategic location that would balance out its lever arm, for instance, and was convenient to the construct of the airplane. So because it's on this large of a scale, I don't remember any issues about left to right balance coming up other than minor adjustments along the way.
Yeah, we did end up with, in its current configuration, we have a slight imbalance being right side heavy. We can easily fix that by just adjusting the fuel load between the left and right wings. And we also do put a little bit of ballast up in the noses, and that's another lever we have to adjust that lateral CG. But excellent question.
Thank you.
All right, Cooper. Maybe you're having some fun, or I'm not sure. Do the wheels go up? Yes, we retract the gear. Maybe we got Stu. An engineer of ours has been leading a rather extensive gear retraction testing in our hangar. It's been quite exciting to see. So we are getting a lot closer to flights where we will be retracting the gear.
While we're waiting for more questions, I do have one. I saw one of the Talon looks like a Dream Chaser. Do you have any plan to launch Dream Chaser?
No, there was a paper done a number of years ago looking at a concept for that and exploring that. But at this time, we've pivoted to focus initially on our hypersonics mission with the goal to get back to launch, space and launch eventually.
Oh, I see. Very good. So folks, this is a wonderful opportunity. So raise your hand, type your question from Sarah.
All right, from Sarah, are there torsional rigidity issues from the center section of the wing, managing via flight controls, etc.? I'll start that question. I'll start to answer that question. Yes, there are concerns, and what our big concern is a differential control input for the pitch. So the horizontal tails, in the event that they go opposite control for some reason, can create an issue. And our safety, we've designed the safety systems to prevent that to the largest extent possible. And our structural margins are definitely in place to help that problem there. So it started off as a more of a design point, knowing going in, because the design team for this aircraft has already had experience with multiple fuselage, twin fuselage configurations. So going into this project, we knew that would be a design point for it. You can actually see some features of the wing itself being a torsional member, as if you look closely at some of the structure in pictures, you can see features that show that we do have structural torsional rigidity built into the airplane wing as itself. And throughout the project, we joked with running very thin guy wires between all these structural components. We knew we couldn't, but we imagined how easy that would make our lives. It did not get to happen though. So in the trades between running a Bronco tail, which is the horizontal stabilizer that connects the top of the two fins, vertical fins, in some of those design trades, that would have helped with that problem. But due to the weight and the build complications of building that high in the air, it was decided that we would accept the risks of that torsional failure by engineering the control system to not fail in a way that would challenge it.
Very cool. Thank you.
All right, anything else for us? Thanks again, Ken. And like I said, the AIAA Los Angeles, Las Vegas section for letting us.
One question here.
Oh yeah, great.
You guys mentioned that you guys went to a partial fly-by-wire setup with the outboard ailerons being by wire and the inboard mechanically cabled. Was that for controllability reasons, or is that for more structural / cabling reasons that was done that way?
Yeah, that was there were a number of reasons. That was an approach we wanted to take. It's the mechanical system, fairly complex as you might imagine, and keeping it tuned and in shape is a not a high maintenance workload, but it's certainly a concern to watch over time. We also had a particular failure mode of the previous design. If we had one of those roll control cables break, it could leave us in a challenging situation. And changing the design to the outboard ailerons being that direct lock man-by-wire removed that whole potential problem. So that was an advantage. It gives us some ability to down the road do some fly-by-wire tailoring if we would like. And it also was a pathfinder into starting to put a command-by-wire or fly-by-wire system into the airplane, which was a great actually stepping stone for the company of building that experience of doing that in-house and putting it in the airplane and having it function. So there were a lot of very good reasons to do that. In terms of the actual flying of the airplane, the authority of those ailerons did not change. Really, it was essentially transparent to the pilots. You put in the same amount of yoke, you get the same amount of aileron deflection. So as a direct handling quality change, not much happened there.
So would it basically give you some redundancy from a safety perspective in case the cables broke? You still will have some sort of at least electronic or electrical control of the outboard ailerons, which of course give you more of a moment arm for roll since they're further out.
Yes,
than your would do. And
yes.
would it also be similar to? I'm not sure. Douglas is probably not the best example, but I'm thinking of Douglas of how like there's certain aircraft configurations where they have aileron as well as horizontal stabilizer trim where you can trim the whole stabilizer, but in the case where the cable, not aileron, but elevator rather, sorry, in case the elevator cable were to fail, the ability to electronically trim the entire horizontal stabilizer will give you some backup pitch control. So would this be kind of analogous or similar along those lines?
It's similar, right? Where you said right at the beginning, it gives us a path of redundancy for certain failure modes. That's really the key to it there. Mm-hmm.
Yeah, keep in mind that we adopted the actuators from the 747, and along with that comes their own built-in failure modes. And our goal was not to modify those actuators, but instead keep them as line replaceable units so that in the event we have one develop a leak or need replacement, it's a direct replacement for our aircraft without the need to modify then test. So with that comes some strange failure modes that you wouldn't necessarily design in from the beginning, but we had to deal with them as a design feature and turn them into our advantage. So in some of those, for example, our outboard versus our inboard aileron sets are literally actuated by the outboard versus the inboard aileron actuators from the 747, and they fail in purposely different ways for advantages of the 747. And also that combines with in the 747, it's part of an integrated system. So in the event you lose an outboard aileron actuator, you actually have an inboard aileron to take over to handle that roll control, along with integrated spoilers that would signal it at certain times. So they had some failure modes that we had to learn and adopt for our own uses. And also our horizontal tail is fixed.
I assume you guys did not implement the spoilers from the 747, right? You guys strictly had ailerons, inboard and outboard.
Mm-hmm.
That's correct.
That's correct. But we did trade those spoilers in early stages of the design, and they were eliminated. And there's still artifacts in our wing that show that we started to build that direction, and we actually abandoned those plans mid-build.
Nice. Final question is, was there ever a plan or path, or is there, to have a manned rocket or spacecraft to be launched under the rock as part of the Stratolaunch, in the future? Is there a pathway for that still, or was there?
We clearly, we have certainly looked at that previously. It's not in our immediate near-term plans, but once we get things going with hypersonic test services, we'll certainly be turning our eyes back towards launch and see where we're at.
To include manned launch as well, not just
it was considered previously. There's certainly some complexities that have to be worked out. So
sure.
So we consider.
Awesome.
Right,
Thank you.
There's also been some joking amongst the engineering and aircrew team about the ultimate party pod you could hang from the middle there, and people around.
All right, we've got a few more questions here, and including a very important one and some friends of the program. So appreciate those questions. So Jim Nelson, a friend of the program. I think this one's for Ivan. Will flap travel continue to be limited to just 2 positions?
Yes, excellent question, and it goes back to what Mason has said many times: the reusability of parts, because our flap actuators are actually landing gear door actuators from the 747. So because of that, they only have 2 positions, up and down. So we would need to basically redesign the actuator system and reinstall that. There would be a tremendous amount of rework to do that. It certainly would be nice to have some intermediate settings, but for our current mission and our current plan, having 0 and 70 degrees works. Again, the 70 degrees seems very extreme, but this airplane, when it's pointed downhill, it's actually fairly slick in terms of drag. And because it's large and heavy, it wants to speed up going downhill. So having those 70-degree flaps are actually a benefit for us.
All right, and this next one, I think, Mason, maybe this is for you. Jacques asks, have we asked Oshkosh to widen their runway yet?
Every time we talk to them. Yep, someday, that's the dream. Actually, to address that for real, we currently operate off of a 12,500 foot long, 200 foot wide runway, which is a standard width runway.
Thanks, Mason. And then from Eric, maybe Mason, you can take the first part, and Evan can take the second part. How sturdy is our mechanical connection between the 2 fuselages via the wing? And then is it necessary to have symmetrical thrust on both sides to prevent a mechanical failure?
Yeah, I'll take that stiffness question, the sturdy question between the mechanical connection between the wing is incredibly sturdy. It is, so the torsional, like I was talking about before, Our wing is designed much like a torsion box, and it in fact is a set of closed boxes for handling torsional loads. And as the wing nears the fuselage and gets close to the root, we actually turn that into shear loads down the sides of the simple flat fuselage panels. And you can see evidence of that by some external metallic features that bolt that together. There have been, along the way, during the buildup of the aircraft, we had to change that design just a little bit as we got into the analysis and understood the different stiffnesses of the wing versus the fuselage and the interaction of the two. But we have very little concerns about the stiffness or the strength of that wing connection, and see it as in fact, I think it leads our mind most of the time.
Yeah, I mean, if I can comment on that from the dirt farmer pilot side, really, if your mental image of this is a general aviation wing that you can flex and move, it is not that. It is a bridge made out of carbon that is between the two fuselages. That's how I look at it as. On both flights we have had, when I've looked out the window and looked at the other fuselage, it was not moving relative to us, no pitch, no shaking. It is steady right there. And on first flight, our chase pilot had been extensively involved with the design of the wing. And there was a lot of, not bets, but a lot of talk about, well, how much is the wing going to flex? How much is it going to move? And he frankly was shocked in a good way at how steady that wing was. It just was solid the entire flight. So it really is it is everyone's favorite question. Of course, you look at the design and go, well, what's happened with that twist in the middle? But the engineering took place to consider that.
And Ivan, would it be fair to say that we don't have to always have symmetrical thrust on both sides?
No, certainly we don't want to be in an asymmetric thrust situation. And we have never and don't currently plan to shut down an engine in flight anytime soon in our flight test program. However, from all this, when we simulate this, a engine out situation in this airplane is practically a non-event. We bring it back to idle, bring the other side matching engine back to idle, and even if you don't do that, you barely notice the asymmetry because you can adapt with the other engines.
Great. All right, another friend of our program asking about the difficulty. Andy, thanks for the question. For the flight engineer to serve drinks in flight, I think he's a pretty accomplished flight engineer, but I'll give it to Evan there.
I would actually like to say something about the flight engineer role. We didn't really talk about that, but it is one of the important innovations in the overall design, which was, again, as Mason said, keep it simple where you can. The Boeing 747-400s that were the parts birds had a lot of automation in them to automate a lot of the control and handling of the hydraulic systems, the electrical systems by just two pilots. In order to reverse engineer that, we essentially would have had to get into the depths of software black boxes and recreate that. Or we could go back to the past and go back to the 747 classic design and have a flight engineer, which enabled us to just use simple, proven technology, hardware connections between all the systems, feeding to a flight engineer panel with nice safety of flight hardware designs. So for us, really having a flight engineer is a huge benefit. Just like it was on earlier airplanes before computers were able to handle a lot of that complexity, rather than deal with designing the computers and that complexity, we just said, well, let's add the flight engineer in, which was the right decision.
Great. Gary has a question for us about, looks like, basically takeoff weight for our first flight and the payload. The payload, we didn't have a payload for either of the flights. I can answer that one. And then the second one, how do we evaluate release dynamics?
Right. So both the flights, our takeoff gross weight was just right around 700,000 pounds. That's roughly 520,000 pounds of airplane and 180,000 pounds of fuel. That is not a full fuel load, so we did a partial fuel load. And interestingly enough, we also took off using less than 60% of thrust on each engine because we didn't need more, and that more thrust in this case would just cause us problems if we did lose an engine. So that's the numbers on the first and second flight. Release dynamics, well, one good thing is the airplane was designed to have a large, free, open space, free of near field and other effects from it. So we've got a pretty clean environment to work with between the fuselages for release dynamics. And we have a whole group of very smart folks working on that. You know, Mason's intimately involved with the release mechanism and the pylon, as well as doing CFD wind tunnel analysis to help build our models for that release dynamics.
Yeah, and I would only add that it's test, test, test. So we model it as much as we can. We start with simple physics, move into more complex physics, and then in the end, it's all about the test.
All right, and then we have looks like Mr. Dale Hoffman has a question.
Yeah, just back again. Did you, was there any wind tunnel testing or did you do all CFD modeling?
I'll let you take it. Yep.
Yeah, Mr. Hoffman, we actually, the airplane, the large airplane itself never did any wind tunnel testing. So it was entirely CFD modeling that was based on, and it did a remarkably good job in terms of first flight. Really, our predictions and our models in the sim were very close to what the actual airplane was. It was really, it was a very pleasant surprise for the flight group.
All right, folks, I think we have time for one, maybe two more questions. Really appreciate all the interest. This is great. Hopefully folks be rooting for us as you hear or see us flying around again. Any other questions we can address?
Well, I would like to say that we are being joined with some teammates. So I'd like to say hi to Cooper and Quentin and Stevie and Powell out there. Thanks for joining, guys.
Still called the Rock?
That is still our nickname, yes.
And that's just mostly for brevity. It's just so much easier to communicate.
I think Dr. Kenneth Zala has a comment. Dr. Zala has a comment. Go ahead.
Ken.
Good evening. Good evening. Can you hear me?
Yes, we can. Thanks, Ken.
A good presentation. I did want to point out that the Society of Experimental Test Pilots in 2019 awarded the Ivan C. Kinchelow Award to Evan Thomas for his professional and outstanding test piloting of this first flight. And that's from the peers of the test pilots in the world. So congratulations, Ivan.
Thanks, Ken. I always felt that I was very fortunate to be recognized in that when I had a team of very smart people, Mason and all the brilliant engineers who built the airplane and the hundreds of shop people who were in there hours, years building the airplane. I just got the privilege of flying it.
Can I get one more?
Yes.
Is there a backstory behind the name The Rock? That was the part I was going to ask. That's the second part of my question. Any sort of mythical connection or something?
Yeah. It's just the Greek mythological character that of the two-headed, what is it, an
It's a
eagle?
giant eagle.
It's a giant eagle and it lifts an elephant, I
Yep,
think.
yep.
Yeah, that's it. There's no more lore or any interesting story behind that nickname. One of the advantages of that name is just it was so short and easy to use, and we knew we'd be writing it down millions of times in the next 10 years of development. So it just made it easy.
Who's going to build the hypersonic test vehicle?
We are. We're building it.
Okay, in the same facility?
Yes.
Okay, you can do it between the wings, right? Or between the fuselage.
That's
Plenty of space.
Certainly, we'll do some testing, but we've actually got a whole second back hangar that's 100,000 square feet where we can build, where we're building those vehicles. All right, well, thanks again. AIAA Los Angeles Launch Vehicle Section. Thanks for hosting us. Mason, Evan, thank you so much. That was great.
Yeah, thank you for the privilege of getting to speak tonight. I appreciate it. Yeah,
Ken, thanks so much for hosting us. We look forward to coming back in a couple of years when we have some more interesting stories to tell.
Anytime. Thank you so much. It's amazing, and we are here to support you, cheer for you, and if anything in between, you know, we have newsletter. We can keep people updated for your great progresses.
Great. Thank you all very much. Have a good evening.
You too. Thank you.